prove this theorem. Firstly, we prove the only if part. If the result is not true, suppose the limit of f is L, and the statement that for any epsilon there is a delta is not true, then there is an incident for any delta. Okay, if this is not true, then there exists some delta 0 positive such that for any delta positive there exists a point in the intersection of A and the delta neighborhood of the point A, removing the center. There is a point, although it's close to the point A, but the value of f is far from the limit L. Fx minus L. Okay, so this is important. How to state the opposite side of a statement. This is logic, very important. Okay. So because this delta is arbitrary, we can take delta. We can let the delta valid along a sequence. So let delta equal 1 over k. K is 1, 2, and so on. The corresponding x denoted by xk. Denote x by xk. We get a sequence. Xk contained in A, but xk is not every term of the sequence, every point in the sequence xk is not equal to A, because the xk is taken from the delta neighborhood of A, removing the center A. So every xk could not be the center A. Okay, but because xk contained in this delta neighborhood of A, and the delta is 1 over k, so the distance from xk to A is less than 1 over k. Okay, so this means that xk converges to A. So we get a sequence such that the sequence xk also satisfies this property. Okay, so fxk minus L is not less than epsilon naught 0. So this implies that fxk could not converge to L. Okay, so this is a contradiction with the assumption that the limit of fx is L. This is a contradiction with this fact. The limit is L. The function limit is L. Okay, because the function limit of L by definition means that any such sequence xk, the fxk, the sequence of functional value fxk should converge to the same L. But we obtained a sequence so that the functional sequence does not converge to L. So this is a contradiction. Okay, this contradiction complete the proof of the only if part of this theorem. Okay, now we prove the if part. So the if part, what's the if part? We assume that for any xk in for the if part, what we do? We want to prove for if part we want limit to be L. This is what we want. For this purpose, take any sequence in A, in the capital A, and xk converts to A. We need to solve fxk converts to L. Okay, if for any such sequence xk this remains true, then this implies by definition, this means that the limit of the function is L. This is what we want. Okay, so to prove that this is true, that is fxk minus L goes to 0. That is the sequence of this sequence of real numbers converts to 0. So by definition, for epsilon positive, by our assumption is that for any epsilon there is a delta blah blah has this property. Okay, so for any epsilon positive, there exists a delta positive such that fx minus L, the norm of fx minus L, less than epsilon for any x in the intersection of A and the delta neighborhood of A, removing the center. Okay, this is the property we know about the function f. Okay, so for this arbitrary epsilon positive, we have this delta. For this delta positive, since our sequence xk converts to A, we can find a capital K. We might find an integer capital K such that the distance from xk to A less than this delta if the index small k is not less than capital K. Okay, but our sequence xk is taken from the set capital K, removing the point small a, and also xk, the distance from xk to A is less than delta. This two fact means that xk contained in the intersection of A and the delta neighborhood of our point A, removing the center. Okay, so by this property, we must have fxk, the distance from fxk to L, less than epsilon. Okay, so this means that for any epsilon positive, we can find a capital K if the index small k is not less than capital K. Then the distance from fxk to L is less than epsilon. So this means that fxk converges to L. So this is what we want. This proves our this result. Fxk converges to L here. Okay. This proves our fxk converges to L here. Therefore, this completed the proof that the function limit, when x goes to A, fx converges to L. The limit of fx is L. This proves out this fact. Okay, so this is the proof of this important theorem. Okay. In this section, we study the partial derivative. partial derivative. In the study of single variable functions, we know that the derivative of a function describes the rate of the change of the function, how fast the function change when there is some difference of its independent variables. Okay, we will generalize this idea, the derivative for single variable functions to multivariable functions. But for multivariable functions, there are so many independent variables. So how to determine the change of the independent variables? We can fix one but other independent variables. Just let one of them change. Okay. So this leads to the concept of partial derivatives. Okay. So to study partial derivative, we need to assume of a function near a point A. Okay. We need the function to be defined over a neighborhood of this point A. Okay. If the function is defined in this set, but A is here on the boundary, at present we don't talk about the partial derivative. Okay, we only consider the case that the function is defined not only on A but also on all points near A. Okay, so for this purpose, we only study the function defined on a neighborhood of A. So suppose f is a function defined on some small neighborhood of a point A. Of course, A is a point in Rn. Therefore, this neighborhood is a n-dimensional subset of Rn. Okay. And we fix an I. We know that fx is fx1 because we are n-dimensional. Therefore, fx is actually x has n coordinate. Therefore, this is in fact an n-variable function. Okay, so we fix I, fix a certain I, maybe ix1 or 2. Anyway, you fix one of them. Fix this I. Fix I. Then we have a single variable function. We have a single variable function defined by Pc. This function is defined on an epsilon neighborhood of the 0. Pct is fa plus TEI. Where EI, what's EI? EI is the basic base element in Rn. The i's coordinate is 1. The other coordinates are all 0. This is EI. Okay. So FA plus TEI, what's this? This is in fact in component case, writing in component wise, this is A1. AI minus 1. The i's coordinate changed. AI plus 1. AN. So from a multivariable function, we restrict the independent variables on a line, on a direction, EI, determined by EI. We obtain a single variable function. Then we can consider the derivative of this single variable function. Okay, so the first step, we obtain a single variable function from a multivariable one.